students, welcome to today's session of academic doubt lectures for the subject advanced structural analysis. So in this lecture we'll see the development of stiffness and flexibility matrix. Am I audible? Am I audible? Is my voice audible? Okay, so let's start with the lecture. So first we'll see the development of stiffness matrix. I've taken the first problem to be like this, right? So there are three. This is a cantilever beam. One end is fixed and the other end is free. Okay, so at the free end there are three coordinates. One is the vertical coordinate, which we have named it as 1. Second one is the moment, which we have named it as 2, and third one is the horizontal displacement, which we have named it as 3. So there are three coordinates here, right? And the Young's modulus I and A. E is Young's modulus, I is moment of inertia, and A is a cross-sectional area of the section, and L is the length of the section. So the length is AB. Now suppose they ask you to develop the stiffness matrix for this. What? Stiffness matrix. Now we want to develop the stiffness matrix for this particular example. Now how we do that is, first see how many coordinates are there. There are three coordinates. So basically when we are developing the stiffness matrix, we see the degree of freedom, right? So all the coordinates can be taken as the degree of freedom. So the degree of freedom is 3 here. Why? Because we have three coordinates at B. So your K matrix will be of the order 3 into 3. So in case they give you coordinates and they ask you to develop a stiffness matrix, this is how you will have to do. Okay, so number of coordinates will be the number of degree of freedom, and the size of the stiffness matrix will be the degree of freedom into the degree of freedom. Okay. Now I shall write the stiffness matrix, what we get here. Okay, so Himanshu, welcome to the class. Ansari, good evening, welcome to the class. Hussein, welcome to the class. Rohan, welcome to the class. Chandana, welcome to the class. Okay, so today we are dealing with development of stiffness and flexibility matrix. So first we are doing with the stiffness matrix. For the same problem I will show you how to do the flexibility matrix also, right? So as I said, 3 degrees of freedom, so the size of the stiffness matrix will be 3 into 3. Now let us write the elements in general term. So this is K11, okay, the second will be K12 and K13, right? Then it will be K21, K22 and K23. The last one will be K31, K32 and K33. Writing this general term is very important. See, now horizontally what you do, keep it as 1. See, K1, K1, K1. Okay, vertically the second term should be 1. Horizontally the first term should be 1. That is how you will have to write this, so that there will be no confusion, right? So once you write this general stiffness matrix, now we have to find these terms. What are these K11, K21, K31? All these things we have to find. One thing you remember, whenever you are developing a stiffness matrix or a flexibility matrix, you have to do it in vertical direction. Okay, you have to do it in which direction? Vertical direction. So whenever you are developing a stiffness matrix or a flexibility matrix, the elements of the stiffness or flexibility matrix you have to develop in a vertical fashion and then put it. Now what does that mean? So this is your first column. Okay, this is your first column, right? Vertically we call it as column, right? This is your second column and this is your third column. So first we'll develop first column elements, second we'll develop second column elements, and in the third we'll develop the third column elements. Right. So first is to get what? To get elements of first column. Right. Now one important thing I want to tell you is, whenever you are developing stiffness matrix, you give unit displacement and see what are the forces developed. Okay, this is very, very important. So when we are developing stiffness matrix, good evening Ramchandra. So whenever we are developing stiffness matrix, we give unit displacement and we see what are the forces developed in the directions of the coordinate. Now what does that mean? Now see here, we are doing first column. So what is the first coordinate we have? We have a vertically upward coordinate, that is our first coordinate. So to get all the first column elements, it is related to your first coordinate. So totally there are 3 coordinates. For first column, it is related to your first coordinate. Now what you have to do is assume this beam. Okay. Now what did I tell you? Whenever we want to develop the stiffness matrix, we have to give unit displacement and see what are the forces developed. In the direction of first coordinate, you need to give unit displacement. Means like this. See, this is the first coordinate, right? So I am giving what? A displacement equal to 1. So basically what I am trying to do, I am giving unit displacement in the direction of coordinate 1. So delta 1 should be equal to 1, whereas delta 2 should be equal to 0 and delta 3 should be equal to 0. What are these deltas? Deltas are nothing but displacements. What are the suffix 1, 2, 3? Suffix 1, 2, 3 are corresponding to this coordinate 1, 2 and 3. So when we are giving delta 1, this is a vertical upward force here in the coordinate 1. So I am giving a vertical displacement like this. So we have to give the displacement and see what are the forces developed. So you have these standard formulas. So in case you are giving a vertical displacement like this, your beam will try to bend like this. Okay. Assalamu alaikum Hussein, welcome to the class. So what we'll do is we'll give unit displacement like this. Now if we give unit displacement like this, we have to see what are the forces developed. There will be reactions developed as well as moments developed. Now what are those reactions? So in this direction, a reaction equal to 12 EI by L cube will be developed. Here the beam is moving upward. Here we have to resist that, so the beam will move downward here. It will be 12 EI by L cube even here. This is the reaction. Now in order to lift this, there will be a moment developed here like this, and in order to get this down, there will be a moment developed here like this. And the value will be 6 EI by L square. Here also it will be what? 6 EI by L square. Understood? So whenever a vertical displacement is given, the reactions developed will be 12 EI by L cube, and the moments that will be developed here will be 6 EI by L square and 6 EI by L square. Right? So now we'll develop this first column elements. Now we have to do K11, K21 and K31. The meaning of this is, see here. If you observe, all the second terms are 1. That is what we are giving unit displacement in the direction of 1. And we have to see, this is what forces developed. These are what forces developed. So if we are giving unit displacement in coordinate 1, what is the force developed in coordinate 1 is what is the meaning of K11. Similarly, your K21 is what? You are giving unit displacement in coordinate 1 and trying to see what is the force developed in the coordinate 2. Similarly, this is what? giving unit displacement in coordinate 1 and seeing what is the force developed in the coordinate 3. Understood? This is the meaning of this suffix terms 1 1 2 1 and 3 1. So basically why we are doing column wise is, in the first column we are giving unit displacement in first coordinate. Okay, so when we give unit displacement in first coordinate and see what is the force developed in the first coordinate. So first coordinate is what? Vertically up. You come here in the blue, whatever I have written are forces. The forces are in the blue color. See now at this point you have vertically up as 1. So here what we have vertically up is 12 EI by L cube. This is also vertically up. This is also vertically up. So the value here will be what? 12 EI by L cube. Understood? Now next, you are giving unit displacement in first coordinate and seeing what is the force developed in second coordinate. You come here in the problem and see what is second coordinate. It is a clockwise movement at B. Come here, do you have any movement? Yes, we have a movement. This is also a clockwise movement at this particular point B. This is point A, this is point B. So both the directions are same. This coordinate 2 and this are in same direction. So the value here will be what? 6 EI by L cube. Understood? Then and the last one is what? We are applying unit displacement in the coordinate 1 and seeing what is the force developed in the coordinate 3. What is coordinate 3? It is a horizontal force at B. If you observe, there will be no horizontal force developed either at A or B because of this displacement delta 1 is equal to 1. Okay, so that will become what? 0. Is it clear everyone? Yes? No? This is standard values. The 6 EI by L square and 12 EI by L cube are standard values. If you are giving a vertical displacement at a coordinate, the reactions developed will be 12 EI by L cube and the moments developed will be 6 EI by L square. Those are standard values. Okay, understood everyone? Yes, please reply if you have understood. Let us move further for the next column. Right, now to get elements of second column, what do we have to do? To get elements of second column, what do we have to do? What do we have to do to get the elements of second column? We'll have to apply unit displacement in the second coordinate and the other coordinates will be equal to 0. The delta 2 and delta 3. Delta 1 and delta 3 will be 0. At the delta 2, you have to keep it equal to 1. Okay. Okay. I guess there was some connectivity issue. Okay, so now let us continue. We give unit displacement. So to get the elements of second column, what we have to do? We have to give unit displacement in the direction of second coordinate. So we have to apply a moment at B, moment of equal to or the moment rotation equal to 1. Okay, so in that case what will happen, how will it look? So this is your beam. So this is your beam. We will give a unit rotation in the direction of second coordinate. So here your delta 2 will be equal to 1. So if you are applying a rotation here, how will it look? This beam will try to bend like this. So we are giving a unit displacement of delta 2 equal to 1. Right. So in this case, what will happen? So the forces developed here. See here we are giving a unit rotation. Now here we had given a unit displacement vertically up, but here we are giving a unit rotation. So what will happen here is the moment developed at this point will be equal to 4EI by L, and at the far end, this is called as the near end, and here this is the far end. Here the moment developed will be equal to half of it, that is 2EI by L. So this is your far end. Okay, so when we are giving vertical displacement, if you observe, the moment developed was 6EI by L square and 6EI by L square, but here we are trying to give a rotation. So when we are giving a rotation, the moments developed will be at the point where you are giving rotation, it will be 4EI by L, and at the R end it will be half of it, that is your 2EI by L. And the reactions developed here, see this, here we have to lift the beam up, here the beam has to come down. So here it will be vertically upward and here it will be vertically downward force, and this will be equal to 6EI by L square. Here also it will be equal to 6EI by L square. Am I audible? Is the streaming happening? Am I audible? Okay, some internet issue. Sorry for the inconvenience. Right, now what did I tell? When we are giving a unit rotation, uh, the moment developed at the point of unit rotation will be 4EI by L, and at the far end it will be 2EI by L. Okay, so the stiffness values that we have to write down are K1 to second column elements, right? K2 2 and K3 2. So what is the meaning? We are applying unit displacement in the coordinate 2 and seeing the corresponding forces that are developed in coordinate 1, 2 and 3 respectively. Right. So you observe now in coordinate 1 we are applying unit displacement in coordinate 2 and seeing what is the force developed in coordinate 1. So coordinate 1 is what? Vertically upward. Here if you come, there is a reaction which is vertically upward. So this will be 6EI by L square, and coming to 2 2. What is the meaning of 2 2? Applying unit displacement in coordinate 2 and seeing what is the corresponding force developed in coordinate 2. Right. So in coordinate 2 there is a clockwise movement here. Here also there is a clockwise moment that is developed, what is the value? That is equal to 4EI by L. Coming to the third one, applying unit displacement into and seeing what is the force developed in coordinate 3. Coordinate 3 is what? Horizontal reaction here. If you observe, there will be no horizontal reaction at this particular point. So this will be what? Equal to 0. Understood? So that is how you have to do. Now coming to the last column element. Now to get elements of third column, what we'll do, we'll apply unit displacement in the direction of third coordinate and see what are the forces developed in the first, second and third coordinate respectively. Right, now for that what we have to do is take the same beam, okay. So take the same beam, what is the displacement in which coordinate we have to apply now? Now we have to apply displacement in the third coordinate. Now what is your third coordinate? What is your third coordinate? Third coordinate is horizontal force at B. So I'll apply a displacement which is equal to delta 3 equal to 1. So if we apply horizontal displacement, there will be only horizontal forces developed. Okay, so axial force or axial force developed. So here the development will be EI by L and here the development will be AE by L and AE by L. Good afternoon, ma'am. Welcome to the class. Sorry, there is some internet issue today, so that's why we are on and off. No worries. I think now it will be stable. So now, right now we'll write the third column elements. So K13, K23 and K33. What is the meaning? So the second terms are what? The second terms are what? The second terms are, you are applying unit displacement in those coordinates. So here we are applying delta 3 equal to 1. And what are the first terms? First terms are, we are seeing what are the forces that will be caused because of the displacement in the third coordinate. So what is K13 meaning? Applying unit displacement in third coordinate and seeing what are the forces developed in the first coordinate. And what is first coordinate? Vertical reaction here. So at this point B, there is no vertical reaction developed because of this displacement. So force will be 0. So here it will be 0. Then again, what is 2, 3 meaning? Applying unit displacement in third coordinate and seeing what is the force developed in the second coordinate. What is second coordinate here? It's a moment. So no moment will be developed. So that will also be equal to 0. And the last one will be what? Applying unit displacement in third coordinate and seeing what is the force developed in the third coordinate. So in horizontal direction, what is the force developed? There is a force which is developed here. This is also rightward and this is also rightward. So it will be what? AEI by L. Understood? So these are your column elements. So now let us assemble it. So your K11, K21, K31, write it in vertical way. So EI by L cube, here we have these values, right? Then 6EI by L square, this is L square. So 6EI by L square and 0. Coming to the next column, 6EI, see here for this column, second column, 6EI by L square 4EI by L and 0. And lastly 0, 0 and AE by L. So this is the 3 into 3 stiffness matrix which you have developed. So basically you need to know the standard values. When there is vertical displacement, the one in the blue are your standard values, reactions and moments. And when there is a unit rotation, the one in the blue here are your reactions and moments. And when there is a horizontal displacement, only horizontal reactions will be developed, that is AEI by L. So if you know this, any kind of coordinate system they give you, anywhere, whatever is the direction, you can develop the stiffness matrix. Now one thing, if you want to check whether your stiffness matrix is correct or no, there is some small way you can do. See, you observe this is a 3 into 3 matrix. So this is what your diagonal elements, right? If you see, if you know already, we have studied that stiffness matrix is a symmetrical, diagonally symmetric matrix. So you observe this element and this element, you're getting same value, 6EI by L square and 6EI by L square. Coming to this, observe here, this is 0, this is 0. Okay, and coming to here, this is 0 and this is 0. So this is a diagonally symmetric matrix. So this is how you will develop your stiffness matrix. Hope you have understood. Now if you want to develop the flexibility matrix, what will happen? You just have to inverse this. So if you want the flexibility matrix, just find the inverse of this stiffness matrix, you will get your flexibility matrix. It's as simple as that. Right. Now let us move to the next problem. I'll do one more problem on development of stiffness matrix. So this is your problem. Now since you already know all the values, it will be quick. We can do it fast. Now you tell me how many coordinates are there here. How many coordinates are there? Yes? Anyone? Total how many coordinates is given? Anyone who want to reply? Totally how many coordinates are given? Yes. So there are totally 4 coordinates that are given. If you observe, the naming is given as 1, 2, 3, 4. So the degree of freedom given here will be 4. So your stiffness matrix will be of the order 4 into 4. If you want to write the general stiffness matrix, so what will it be? K11, we'll write horizontally, K11, K12, K13 and K14. The first terms should be same. Then it will be what? K21, K22, K23 and K24. Then K31, K32, K33 and K34. And the last will be what? K41, K42, K43 and K44. Right, this is the general term. Now let us start developing one by one. So first is what? To get elements of first column. Always remember, you please do column wise, right? So if you want to get the elements of first column, what you have to do? You have to apply unit displacement only in the first coordinate. In the second, third and fourth coordinate, the displacement should be equal to 0, right? So what is the first coordinate here? It is a vertically upward reaction. So how will your beam look now? Okay, so if this is your, we can assume it as fixity and do, because the reactions what we develop are assumed as fixed, right? So in this direction 1, we have to give unit displacement. So delta 1 equal to 1. So if you give unit displacement in this direction, I will erase the arrow. Arrow is not required. So I am giving unit displacement. So how your beam will bend? Your beam will bend like this. So when you are giving vertical displacement, what are the reactions developed? The reactions developed standard value we have just now seen. So it's what? 12EI by L cube. See here the beam is lifting up. So this should be upward like this, 12EI by L cube. And here it will be, the beam should be at this position. So it should be lifted down. So 12EI by L cube. And what will be the moment developed? 6EI by L square. So here we have to lift the beam up. So this will be the direction, 6EI by L square. Now here we have to get the beam down. So the direction will be, you have to be very careful with the directions, or else your signs in the stiffness matrix will go wrong, right? So because of this unit displacement delta 1 equal to 1, the reaction forces developed at this point A and B are as follows. Now let us write all the values. So first let us write K11, K21, K31 and K41. What is the meaning of all these terms? We are applying unit displacement in the coordinate 1 and trying to see what are the forces developed in these coordinate. Okay, K11 is what? So in at 1 coordinate 1, what is coordinate 1? Vertically upward reaction. Here also we have a vertically upward reaction. What is the value? 12 EI by L cube. Next K21. 2 is coordinate 2 is what? Anti-clockwise. Okay, let us name this as A and B. Anti-clockwise movement at A. Come here. See if there is a moment. Yes, there is a moment. This is also anti-clockwise. So how much is the moment? 6EI by L square. Next, third coordinate. What is the third coordinate? Vertically upward reaction at B. So here, if you observe, there is a vertically downward reaction. So what will happen here? What should you write? You should write minus 12EI by L cube. Why minus? Because the reaction developed and the coordinate are both in opposite directions. That's the reason you will get a minus here, right? The last one is what? 4, K41. So you have to see coordinate 4. So coordinate 4 is what? Clockwise movement at B. If you observe, there is an anti-clockwise movement developed here. So that will be minus 6EI by L square at K41. Understood? So hope everyone is able to understand it. Now let us move to the elements of second column. Hi Mohana, welcome to the class. So to get elements of second column. Now what we have to do to get the elements of second column? Only in the direction of second coordinate we have to take the displacement equal to 0. In all other coordinates we have to keep it only in the direction of second coordinate we have to keep the displacement equal to 1, and in all the other coordinates the displacement should be equal to 0. Mohana, can you make videos on maths? Actually for maths for Ekeeda I am not the in charge. Already there are maths classes which is being conducted, so you can go to the Ekeeda page and see maths classes also are being conducted for engineering mathematics subjects. Okay, I will be responsible only for the advanced structural analysis subject. Okay, anything from advanced structural analysis, if you want any topic, please tell me so that I can take a session on that particular topic which you want. Okay, so today's is development of flexibility and stiffness matrix. Right, now what we are doing to get second column, we have to apply displacement in the second coordinate. Now let us see how will we get it. Right. So what is the second coordinate here? Second coordinate is anti-clockwise movement at A. So if you apply a anti-clockwise movement, so like this unit movement or rotation we can tell. So if you apply unit rotation like this, that's your delta 2 equal to 1. How will your beam bend? Your beam will bend like this, right? So this is delta 2 equal to 1. Now as I told you, when vertical displacement happened, these were the reactions developed. Now when a rotation is given, what are the forces that will be developed? We have already discussed here. So the forces developed will be what? 4EI by L and 2EI by L. So at the near end where you are applying the displacement, so this is your near end, this becomes your near end and this becomes your far end, right? So here the moment developed will be equal to what? 4EI by L, and here the moment developed will be what? Half of it, that is 2EI by L. So whenever you are giving a unit rotation, these are the moments developed, right? Be careful with the directions. Now we have to lift the beam here as it is, we have to put, now here we have to put the beam down, so that's the reason I have given an anti-clockwise movement here. Now similar to that reaction. Now there will be a reaction like this here, and here there will be a downward reaction because we have to get the beam down. So what will be the reaction value? It will be 6EI by L square here as well as 6EI by L square here, right? So these are the forces developed because of delta 2 equal to 1. So let us write the element values now. So what are the element values? So it's K12, K22, K32 and K42. What is the meaning? Applying unit displacement in the second coordinate and trying to see what are the forces developed in the first, second, third and fourth coordinates respectively. So let us see first coordinate. What is first coordinate? Vertically up at A. Here also we have a vertically upwards value which is 6EI by L square. Then second coordinate, so it is anticlockwise movement at A. Come here, yes, we have an anticlockwise movement at A which is 4EI by L. Then coming to the third coordinate, what is it? Vertically upward force at B. If you come to B, there is a vertically downward force. So what will happen? Only thing is you have to change the symbol, right? So because it is both are in opposite directions, it is minus. Last one is what? Anti-clockwise. No, this is clockwise movement at B, whereas here at B we have an anti-clockwise movement, so that will be minus 2EI by L. Hope you all are understanding it, right? Now this is your second column element. Now let us go for the third column. So to get the elements of third column, what we have to do? What we have to do to get the element of third column? Only delta 3 we need to take it as 1 and all other displacements we have to keep it as 0. So only in the direction of third coordinate we have to give unit displacement, right? So how will it happen? So this is your beam. What is your third coordinate? What is your third coordinate? Vertically upward reaction at B. So you have to give a vertical displacement of delta 3 equal to 1. So if you give like this, what is the moment? The moment developed will be like this, right? So if the moment developed is like this, so here it will be what? You have to lift the beam up. So here it will be 12EI by L cube and here it will be what? 12EI by L cube. And the reactions will be what? So here we have to get it down. So 6EI by L square. See, standard, if there is vertical displacement, these are standard values. Here you have to lift it up. So it is what? 12EI by L cube, right? So if I want to write the elements, K13, K23, K33 and K43, right? What is the meaning of this? We are applying unit displacement in third coordinate and we are trying to see what are the forces developed in the first, second, third and fourth coordinate. Now let us see one by one. So first coordinate is what? Vertically upward force, but here there is a vertically downward force. So this will be minus 6EI by L square coming to 2, 3. So second coordinate is what? Anti-clockwise movement at A, but here we have a clockwise movement. So again it will be minus 12EI by L cube. Coming to the third coordinate. So third coordinate is what? Vertically upward reaction at B. So here what we have? We have again vertically upward. So both are upwards. So that will be 12EI by L cube. And the last one will be what? Clockwise movement at B is the fourth coordinate. Here also we have a clockwise movement. So oh sorry, this is wrong. Yes, here I have done a mistake. This is 6EI by L square. Reaction is 12EI by L cube, whereas the moment developed will be 6EI by L square. In the hurry I have written. Okay, so 3 3 is what? 3 3 is vertical. So this is 12EI. I think this entire thing is wrong. I'll just change it. So coordinate 1 is vertical reaction. So vertical reaction is how much? here also I've written it wrong. Okay, so vertical reaction is 12 EI by L cube and the moment developed is 6 EI by L square. I've written it wrong. Okay, so here the reaction is upward, here it is downward, so minus 12 EI by L cube. Moment is anti-clock here, whereas it is clockwise here, so plus 6 EI by L square. Then coming to the third one, upward reaction at B is the third coordinate. Here also we have a upward reaction, so it's plus 12 EI by L cube. And lastly, the moment is clockwise here at coordinate 4. Here also there is a clockwise moment, so it is 6 EI by L square. Right. So now the last column. Now to get elements of fourth column, what we have to do? We have to apply unit displacement in the fourth coordinate, whereas all other coordinates we have to keep it as 0. Right? So all other coordinates, let us keep it as 0 and see how the diagram will look. So it will look similar to your, we are applying unit moment because the fourth coordinate is a moment here, right? It will look similar to your second coordinate. Right, let us put the beam and apply a unit rotation in the direction of the fourth coordinate. So here what is it? It is a clockwise movement at B. So if you want to put a clockwise movement of delta 4 equal to 1, this will lift the beam like this and like this. Right, so here we are giving a unit rotation equal to 1. So if you give unit rotation equal to 1 here, what are the forces that will be developed? Standard values. If you are giving unit rotations, what are the standard values? The moment at the near end will be 4 EI by L and the moment developed at the far end will be 2 EI by L. This is your far end. This is your near end. What is near end? The point where you are applying unit displacement, right? And what are the reactions developed? The reaction developed will be 6 EI by L square at both the places. So here also it is 6 EI by L square. Right, now let me write the values. I'll write it here. Okay, so K14, K24, K34 and K44. What are the meaning? You are applying unit displacement in the fourth coordinate and trying to see what are the forces developed in the first, second, third and fourth coordinate. Right, so let's write one by one. So in the first coordinate, vertically upward force, whereas here there is a vertically downward reaction, so minus 6 EI by L square. Then anti-clockwise movement is the second coordinate, whereas here there is a clockwise movement, so it is minus 2 EI by L. Next, coming to the third coordinate, vertically upward at B. Here also it is vertically upward at B, so it's 6 EI by L square. And the last one will be what? Clockwise movement at B. Here also there is a clockwise movement, that's 4 EI by L. Now let us assemble all, let us write all the values here. So you have to write what? Column wise, right? So let me start. So this is your first column elements. So 12 EI by L cube, then 6 EI by L square, minus 12 EI by L cube. The last one will be minus 6 EI by L square. Next, second column, here we have second column elements. So 6 EI by L square, then 4 EI by L, then minus 6 EI by L square, and the last one will be minus 2 EI by L. Next, third column. Good afternoon, Bhaskar. Welcome to the class. Now third column. Where are the third column elements? Yes, here we have the third column elements. So minus 12 EI by L cube, then 6 EI by L square, 12 EI by L cube, and the last is 6 EI by L square. Then last column elements which we have written here. So minus 6 EI by L square, then minus 2ei by L, then 6ei by L square, and the last one will be 4ei by L. Right, so this is the 4 into 4 matrix, stiffness matrix, which we have developed. Now let us just have a quick check. So I will encircle the diagonal elements. So these are your diagonal elements. Now see, on the other sides of your diagonal elements, you should get symmetric, right? You should get same values. See here, this and this same value, 6ei by L square, coming to this minus 12ei by L cube, minus 12ei by L cube. Then here minus 6ei by L square, minus 6ei by L square. Right, moving on to this 6ei by L square, 6ei by L square. Here minus 2ei by L, here also minus 2ei by L. Now here there is some problem. Let us have a quick check. See, here you have a minus, but here you have a plus. So we have done some mistake, or else you will not get like this. It should be a diagonal symmetric matrix. Good, it was a mistake, so that now we can identify and correct it. Whether it's minus or plus, we'll just have a quick look. So this is second row, third element. So second column, second row, third element. Let us have a check. Now what is third coordinate? Third coordinate is vertically upward force. Okay, but here it is a vertically downward force. That's the reason we wrote it minus. Okay, done, correct. Now come to third column, second element. So third column, second element is this. Okay, so second coordinate you need to have a look. Come here, second coordinate, to push it down. Okay, in order to push it down, we will need a clockwise movement. Yes, so here it is anti-clockwise. See, observe, here there is a clockwise movement at A, but here there is a anti-clockwise movement at A. So what will happen here? It should be a minus sign, right? So this was minus here. So now it became same. So that's how they will be diagonally symmetric. You just have to recheck it, because the problems will be little lengthy and the plus sign and minus sign will be difficult. You have to be very careful. So you, after writing, have a final look. Now as we saw, we came to know the mistake because it was not diagonally symmetric at one point. So we just checked and corrected which was wrong, right? Now if you want flexibility matrix, what you do? You just find the inverse of this 4 into 4 matrix. You will get your flexibility matrix. Understood? So these are some of the example. If you want many more examples on the development of stiffness and flexibility matrix, you can go to the Ekeeda app, right, and see there for the subject advanced structural analysis. I have a total of 117 lectures, where we have covered the entire stiffness matrix, flexibility matrix, then modified moment distribution method, then your column analogy method, Miller's-Bessler's principle, whatever is there in your advanced structural analysis subject, that is covered here. Right, the one more name for this subject is indeterminate structural analysis. Normally this will be an elective subject in your curriculum. So people who are really want to go to study structures further, so it's a very important topic which you have to take up. Okay, so let's move further. Now as you know, the development of stiffness matrix, you can now, for whatever is the coordinate given, you can develop the stiffness matrix. Now there are some standard values. There are two types of approaches. This we have already discussed, I guess. So in stiffness method, there are two types of approaches. One is transformation approach and one is the direct stiffness method approach. So in that, we will use a standard stiffness matrix and standard flexibility matrix. We don't have to develop for every problem. When we are doing analysis of structures by either stiffness method or flexibility method, we can use the standard formulas. So I've just shown you some standard formulas. So if you're going for transformation approach of stiffness matrix, we can use two types of stiffness matrix. One is, if you take both of these rotations as clockwise, if you take both of the rotations as clockwise at both ends, you will use EI by L 4 to 2 4, and if it is anti-clockwise, it will be same, EI by L 4 to 2, 4. Hi Jaktar, welcome to the class. Okay, so this is the standard you will be using. If it is transformation approach, whether it's clockwise movements as the coordinate or anti-clockwise movements as the coordinate, the standard stiffness matrix what we use is EI by L 4 to 2, 4. This will be a 2 into 2 matrix only. Why? Because we take individual element, and for individual member or element there will be only 2 local coordinates. That's why it will always be a 2 into 2 matrix. If you go for direct stiffness method, it will be a 4 into 4 matrix. Just now what we have developed. This is what we have developed just now. Here, this we have taken EI by L square common, EI by L cube common. So if we take EI by L cube common, this is the matrix which we'll get. This is the one which we'll be using in the direct stiffness method. Okay, so this is the standard value if you are using direct stiffness method. Again, there are two approaches. The first approach is what? Vertically upward. These two will be vertically upward coordinates, whereas the rotations will be clockwise. In that case, only the first row and first column, see, first row and first column except the diagonal element should be taken as negative. The other option is what? Again, here both the reactions are vertically up, whereas the rotation is anti-clockwise. If in case we are taking this approach, the third row and third column except the leading diagonal element should be negative. See, observe, this is the third column, this is the third row. The third column and third row should be negative. If it is anti-clockwise rotation you are assuming. If it is clockwise rotation you are assuming, you will take this and this as negative. These are the standard values of stiffness and stiffness matrix which we will be using for transformation approach, and this is for your direct stiffness method. So when you are solving problem on stiffness method, analysis of structure by stiffness method, you either do it by transformation approach or you do it by direct stiffness method. One of these steps is finding the stiffness matrix, wherein you don't have to develop the stiffness matrix from the start. You can just directly use these values. Now how we got these values? We have just now seen and derived it. Okay, you can even derive it for this case. This case is also easy. There are only two coordinates. So apply unit displacement in one coordinate and see what are the forces developed in these two coordinates, and you will be able to get it, right? So flexibility matrix, you should do it in the same approach, right? I will just show you the standard flexibility matrix which we will be getting. Right, actually I wanted to do problem, but because of the time constraint we will not be able to solve the flexibility problem, right? So I'll just show you the standard value. Now these are the standard value. In a flexibility method you don't have a direct approach, you just have transformation approach. So the standard case for the transformation approach can be taken into two concepts. One is the moment concept. So if you're going with the moment concept, there are two things here, both clockwise and both anti-clockwise. If they are both clockwise or if they are both anti-clockwise, it doesn't matter. The flexibility matrix will be what? L by 6EI 2 minus 1 minus 1 2. If you inverse this, you will get your stiffness matrix, or if you inverse the stiffness matrix, you will get your flexibility matrix, right? This is the standard value which you will be using. Whether it's both clockwise or both anti-clockwise, this is the formula for moment concept. If you are going with bending moment concept, then sagging and hogging will come. If this coordinates are creating sagging moment, then it is 2 1 1 2 L by 6EI. If it is hogging also, it will be 2 1 1 2 L by 6EI. See, there is a slight difference when you go with moment concept and when you go with bending moment concept. In bending moment concept, there is no negative sign, whereas in moment concept, if you observe, there is a negative sign here. If you develop the stiffness matrix, you will come to know why this has. If you develop the flexibility matrix, you will come to know why this has come. Okay, so this is all about your development of flexibility and stiffness matrix. So if you want more details on this, you can go to the Ekeeda app and take up the subject of advanced structural analysis. If you install the app, you will get 1000 free points. So that's equal to your 1000 rupees. So you can purchase any course you want. All the courses related to civil engineering is there or any other branch of engineering is there, or as well as recently we have launched the what is that gate syllabus also. So individual subjects you can take, or you can take it as a whole package. Any doubts you have, please ask. Any doubts? In the next session, actually today I had to solve the analysis using stiffness method, but I thought development of stiffness and flexibility matrix should be taught first. So today I took up this topic. In the next Saturday 4 o'clock session, I will be solving a complete problem on stiffness method. So how to analyze a structure or a beam using stiffness method, that I will be explaining. Okay, so any doubts? Anyone, any doubts, or shall we end the class? Any doubts, please comment. Yes, I guess there are no doubts. So let us end the class for the today's session. In the next session, we will meet again next Saturday 4 o'clock, to discuss on a problem or analysis problem on the stiffness matrix method. Okay, so thank you for attending the class. Hope it was informative.